Hello everyone, my name is Yu-Qian, come from Fudan University. I'm here to present our work, the depth-guided adaptive mental fusion network for feature video recognition. First, I would like to introduce the task of feature video recognition. Feature video recognition aims at recognizing the action of the query video when only one or few examples are given. Concretely, given a query video, you need to tell what the action category it belongs to according to the videos contained in the support set. In an n-way causal setting, there are n classes in an episode. For each class, k-labeled examples are given. This figure also is the illustration of the three-way two-shot problem. Many works have been done to address the few-shot learning problem in the image domain. However, few-shot video recognition still remains underexplored. Recent efforts, including learning from web data, constructing key-value memory network, matching videos by temporal alignment strategy, and so on. Different from these works, we mainly tackle the data scarce problem by exploring the depth information. In this paper, the depth map is introduced as the carrier of the scene into our model. As shown in this figure, we mainly observe two important characteristics. First, it's obvious that the scene information helps us to recognize the actions. In this example, the mountain is critical to identifying the action as riding mountain bike. The second point is that even though the scene shifts from the mountain to the road side, we can still recognize the action correctly. We argue that a robust model should also have the ability to tolerate such inconsistency. So, the first question is how to use the information contained in the depth frames. In order to solve this, a novel depth-guided adaptive instance normalization module is proposed to efficiently fuse the features of the RGB modality and the depth modality. Before introducing our depth-guided add-in, I want to give a brief introduction to the instance normalization. The instance normalization is first proposed for style transfer. This is the result generated by add-in, which is a flagship work of image style transfer. Add-in takes a content image and a style image as inputs and generates a new image set keeping the content unchanged as the former image while transferring the style to the later image successfully. Such a phenomenon inspires us to think that if we replace the content image to the RGB feature map and replace the style image to the depth feature map, then feed them to a familiar instance normalization module, what would happen to the fused feature map? The initial instance normalization is defined as follows. The input X has the size of B times C times H times W, which is decided for the image. Here the mu and sigma are the mean and the standard deviation of the input X, while gamma and beta are fair parameters ranged from the input data. Correspondingly, for our depth-guided add-in, the input has the size of B times D times L, whether for RGB features or depth features. Here the D denotes the number of frames contained in a single clip, while L denotes the dimension of the feature for each frame. Again, the mu and the sigma are the mean and the standard deviation of the input RGB feature. Notably, we change the gamma and beta to the functions gs and gb, which takes the depth features as input, so that we can learn the parameters from the depth information. In this paper, both G and GB are set as a fully connected layer. In this way, we fuse the features from the RGB and the depth with the expectation of keeping the content of RGB unchanged while defining the feature towards the depth. The second question is how to improve the robustness of our model. As stated above, our humans can tolerate a certain degree of inconsistency. Based on this observation, we propose a novel temporal asynchronization augmentation strategy as an advanced data augmentation method. Inspired by the TSN network, which handles long-term videos well, we propose a basic sampling strategy to handle the video input. Given a video, we first divide the frames into non-stack segments of equal length. Then, non-frame consecutive frames are sampled from each segment to form the final sampled clip, which will be fed into our network. As for sampling for multimodality data, the most natural way is to sample the strictly matched clip, as shown in this slide. In fact, most of the multimodality fusion methods sample data in this way. However, we not only sample the matched depth clip for RGB, but also sample other non-org pairs by randomly sample consecutive frames from each segment. By feeding our network with such unmatched pairs, our network is expected to be more robust. This is the overall framework of our network. Generally, it's designed as the two-string architecture. The RGB string extracts the more generic facial information of the input videos, while the depth string provides supplementary scene information. Our depth maps are obtained by using the off-the-shelf depth estimation model termed as Memo Depth 2. For both strings, we adopt the ResNet 50 network operating on ImageNet as the feature extractors. The output of the last fully connected layer, which is a 2048 dimension vector, is extracted for each frame in the clip. Then the RGB features and the depth features are fused by our depth-guided add-in module. Finally, the ProtoNet is selected as our future classifier. We train our model under the mental learning mechanism, which consists of the mental train and mental test stages. The episode-based training strategy is adopted to train our network. Each episode contains a support set and a query set. The model means to inference the query video according to the videos in the support set. Besides, we follow the n-way causal setting, which has been introduced above. During the mentoring stage, we sample the unmatched pairs by temporal asynchronization augmentation strategy proposed by us. The cross-entry file is used to calculate the loss, thus optimizing the network. While during the mental test stage, only the strictly matched RGB and depth pairs are sampled. The action class with the highest probability is selected as the predicted class. We conduct experiments on 3 widely used datasets for video recognition, including Kinetics, UCF101, and HNDB 51. Notably, there are non-overlapping over the classes of the training set, validation set, and the testing set. This is the recognition result on the Kinetics dataset. Comparing the result of RGB BaseNet++ and ours, we can observe that the depth information does help us to recognize the actions. Comparing the result of the last two laws, of which the only difference is whether the temporal asynchronization augmentation strategy is used to train the model, we see that this augmentation strategy improves the robustness of our model. Most importantly, our full model outperforms all the baselines and competitors. We also conduct experiments on USF and HNDB. Our method achieves the state-of-the-art performance on all the settings. We want to highlight some other results. First, we notice the performance improvement between the two baselines. RGB-BaseNet samples 16 consecutive frames from each clip, where RGB-BaseNet++ adopts our basic sampling strategy, which samples more sparse frames. Thus, we can capture more temporal information. Besides, the actions contained in USF are much easier to recognize than that of HNDB, since HNDB contains some challenging facial actions such as smile, laugh, and talk, which is very hard to distinguish. To provide a more intuitive feeling, we visualize the class activation map of some examples sampled from the validation and testing set of the Kinetics dataset using the ground cam. In particular, the gradients of the action with the highest probability are backgrounded to highlight its map of interest. The results of the RGB submodel, the depth submodel, and our full model are demonstrated in the last three columns, respectively. We see that the RGB submodel outperforms the depth submodel, which is consistent with the fact that the RGB modality contains most of the facial information. Also, the depth submodel doesn't seem as good as that of the RGB submodel. The performance of the RGB submodel is improved by introducing the depth modality. We note that our full model not only recognizes the important regions correctly, but also eliminates the noises brought by irrelevant backgrounds to a large extent. We also conduct some ablation studies on fusion strategy, fusion modules, and temporal shifting turns. Experimental results show that our proposed depth-guided add-in outperforms concatenating the features together directly. And using the depth feature to guide the RGB feature seems the best choice. As for the temporally shifting mechanism, when we set the non-sec as 2, which means we shift the depth modality for 2 turns, our model performs best. Finally, we summarize our contributions here. For the first turn, the depth information is used to alleviate the data scarce problem in future video recognition. Secondly, a novel temporal asynchronization augmentation mechanism is proposed to augment the video representations. Thirdly, a novel depth-guided adaptive instance normalization module, which termed as depth-guided add-in, is proposed to fuse the multimodality features. Finally, our proposed full model establishes the new state-of-the-art on 3 widely used datasets, including Kinetics UCF101 and HNDB51. Okay, that's all. Thanks for your attention.